systems
of equation using
elimination. What? How did you guess that?
Because there's the thing over there in the venti.
Yeah.
Oh, that's crazy. All right, so the other crazy thing is that I never filmed myself writing up the title, but I just filmed it, and you guessed it. So it's on film, confirmed that you guessed the title. All right, systems of equations using the elimination method. So systems elimination. All right, substitution was really nice for solving systems when they looked like y equals, right? When they were in other words, slope-intercept form. But we all know that not all equations are written in slope-intercept form. And so you can make them say y equals or x equals, right, with a little bit of work subtracting things over. Or you can use this other method. And it's called elimination because of the very first step, usually. And today I'm going to show you one version of elimination. We're going to go a little bit more in depth with it next week. Okay? So let's look at a problem like this. 3x minus 5y equals 1. 4x plus 5y equals 3. Okay. So if we were to try to get this into like y equals or x equals, if we were to try to isolate one of these variables, it would be a lot of work and we'd have fractions, right? I could do it. I mean, I could add 5y to both sides and then divide both sides by 3. So I would end up with x equals 5y plus 1 divided by 3. That's kind of a weird fraction that I'm not super excited about plugging that into my other equation. I could do it. It would totally work. Right, or I could isolate y. But if I isolated y, then I would have like y equals negative 1 plus 3x divided by 5, right? Something like that.
Divided by negative 5, right?
Well, because I made the 1 negative.
Oh,
I like move the 1 over.
Yeah.
And I'm just doing that in my head, but it's not like a pretty thing to plug in. It's not going to be a lot of fun to plug that in. However, these two equations are perfectly set up to use the elimination method.
Because one's minus 5y and one's
Exactly. That's what I'm looking at. The elimination method is eliminating one of the variables by adding your two equations together. And the fact that we can do that is kind of weird.
Oh, yeah.
But let's think about it. If I had an equation like 4x plus 5y, I can add 1 to both sides of this equation, right? That's allowed. So I could add 1 here and add 1 here. But wait a second. 1 is equal to 3x minus 5y, right? So couldn't I just add 1 to this side and add 3x minus 5y to this side? I could, because it's the same thing. I can actually add equations together because of that same like golden rule of algebra. You can add something to both sides of an equation. So if I add an equation to another equation, I'm adding something that's equal to both sides of the equation. So that's kind of the justification. We're not going to go into like a proof or look at the reasoning behind that, but you could just take my word for it for now. I can add two equations together. It's allowed. So I like to draw a line when I do this. And these equations are lined up. So I have my x's above my x's, my y's above my y's, constants above constants. I like to, if they're not lined up already, I like to line them up before I do this. And then I just add. So 3x plus 4x is 7x. Negative 5y plus 5y, that eliminates. And that's why we call this the elimination method. The whole reason that I can add these equations together is because I eliminated y. So 7x equals, and then I have 1 plus 13, which is 14. How do I solve this?
Divide both sides by 7.
Yeah, go ahead. Divide both sides by 7. X equals
2.
dos. Or 2. I'm done.
No.
No, why am I not done?
Plug it in.
Plug it in. Which equation should I plug it into?
Anyone.
Doesn't matter. Yeah, it doesn't matter. Let's plug it into the top one. So then I have 3 times 2 minus 5y equals 1.
6 minus 5.
Okay. 6 minus 5y equals 1. Subtract 6 from both sides.
Negative 5y equals
Negative 5y equals negative 5.
So y is equal to 1.
So y equals 1. Let's check it. So I think the answer is 2, 1. How did I find y? Did I use the first equation or the second equation? I plugged it in here. I used the first equation. Let's check it in the second equation. So I'm going to say 4 times 1 plus 5 times 2 equals 13, right?
No, that's wrong. It's the other way around. Yeah. Equals.
Oh, yeah. So 13 equals 4 times 1. Is that what you're saying? The other way around?
Does that matter?
Because x equals 2. Yeah.
X equals 2, yeah.
That's why.
Oh! That's why. Oh, I have to be careful, huh, when I plug things in. X was 2. And y was 1. Was that right?
Yeah.
Okay. So now let's see if this is true. 4 times 2 is... What's 4 times 2?
8.
8. Plus 5 times 1?
5.
Does that equal 13?
13, yeah.
Check. So my answer is 2, 1. Questions? Questions on that process? No?
Can you make it so it says like negative 5y and 5y?
We're not going to do that today. Let me just double check on your homework. But yeah, on that homework they will all equal. I mean, they will all have that set up for you. But yes, the short answer is you can do that. Okay, let's do another example. You guys talk me through it. You guys talk me through this one. So let's say I had something like this. 3x minus 7y equals 8. And let's say 5x plus 7y equals 0. Okay, what's my first step?
Add 3x and 5x.
Yeah, I'm going to add the entire equation. So first part of that is adding 3x and 5x, which is,
8x. And then you can eliminate the y.
so 7y and 7y eliminates, because this one's negative,
Good equal to 8.
equals 8. So x equals,
No, you have to divide by 8.
divide both sides by 8, x equals 1.
1. And then plug it into one of those.
Plug it in. Which one do you want to plug it into?
Anyone.
Okay, first one. So 3 times 1 minus 7y equals 8. What do I do now?
Wouldn't that just be 3 minus 7?
Yeah, it's just 3 minus 7y equals 8, because 3 times 1 is just 3.
And then subtract the 3.
Subtract the 3. What do I have?
And then you have Negative 7y.
Negative 7y, very good.
5.
Equals 5.
And then you have to divide by 5.
Divide both sides by 5.
No, divide both sides by -7.
Oh, divide both sides by negative 7. So y, we'll just leave it as a fraction, equals negative 5/7. Wait a second. Is that possible?
Yeah.
Can y be a fraction?
Yeah.
Yeah, that's fine. So we've got 1 negative 5/7. It even wouldn't be that hard to plug this in and check it because I have 7y, so the 7 is going to cancel with the 7 here. So I would have 5 times 1, which is 5, plus negative 5, because the 7s would cancel, equals 0. So 5 plus negative 5 equals 0, is that true?
Yeah.
Yeah, it is. It's the same thing as 5 minus 6. So it would check if we wanted to do that work.
Would you use this system of equation more than the other one?
It's a really good question. I find myself using elimination more, but I think I'm wondering if it's like partly just personal preference of like which one you like better. I don't know. Like when it comes to systems word problems, a lot of times it's not very hard to set them up as substitution problems, but I just tend to use elimination, I think. I don't know. When you get into like algebra 2, you'll see 3 by 3 systems, and elimination is almost always used to solve a 3 by 3 system. No, there aren't very many 3 by 3 systems that you can solve only with substitution. But you will use substitution to solve them also. You'll use both. Okay. So, questions about elimination method? Yes. Solving systems of equations. So,
Well, yeah, but what are systems of
what are they used for?
When you have 2 variables?
Yeah, it's a little tricky to say. There's not like one thing that they're used for, but if you can turn a problem into 2 separate equations, then you can use a system to solve it. So like, I think I gave you guys this example. One example is if you're plotting the trajectories of 2 objects,
Yeah.
right, and you want to see where would they actually hit, right? So you could imagine it as some sort of like a military or a Navy exercise or something, right? Where they're saying, well, my missile goes here and the plane is here, where will they actually hit? Or will they actually hit? Or you could imagine it as an object going into space, a space shuttle taking off from Earth and the moon orbiting the Earth. How do we design that space shuttle's trajectory so that it intersects with the moon at exactly the right moment in time?
Wouldn't that be more complicated?
That would be very complicated.
Yeah.
Yeah. It wouldn't be a 2 by 2 system, I don't think. Because you have other variables, like you have the variable of time, right? You have 3 dimensions to work with, that sort of thing. But then also, if you can represent things as linear functions, even if they're not technically like lines or graphs, so you'll often see, like in economics, you'll see a function of supply and demand. I don't know if I'm doing those right, but like usually as supply goes up, demand will go down, but there's always a point where supply and demand intersect. So that's technically a 2 by 2 system of equations, is finding that point where those 2 things intersect. And if you're designing a business, you would kind of want to know what that point is, so you would know how many of your product to make. Because if you make too many, you wouldn't necessarily sell them all. Or you'd have to sell them for too cheap. If you made just the right amount, you'd hit that intersection. And then you'll see tons of word problems that use systems of equations. Like we could use them for age word problems. We use them for those coin word problems. We can use them for like attendance word problems. So sometimes you'll see a problem that's like You know, adult tickets cost $15 and youth tickets cost $8.
Oh, I hate those problems.
If a theater sells $372 worth of tickets, and you know they know that 17 adults attended the performance, how many youth tickets did they sell, or something like that. So then you can actually take those words and turn that into two equations that you then solve. So I find systems of equations to be tremendously useful for solving word problems, because what you can do is you can just look at a word problem and try to just think of one equation for each sentence. And then often you can combine those equations as a system to solve. It doesn't require, like, I was never taught when I should probably stop this video in a minute, but I was never taught when I was taking math how to solve like distance word problems or age word problems. These things that Gary has developed these tables to solve, I was only ever taught systems of equations. But you can solve all of those problems, distance and age, as systems of equations. You can use a system to solve those. It becomes a little bit more complicated, and sometimes it actually is a 3x3 system, but it's a simple 3x3 system that you can use substitution to solve. So, I don't know, it's partly like a way of thinking, I think, in terms of you see a word problem, can you now think of it as a system? And you think of the different linear relationships within that word problem and then combine them to find your answer. And we will get into some more applications of like word problems that might use these